Okay, so question 3 then was electromagnetism, and we were given this diagram here. So it's talking about the motor inside here, making use of the motor effect. So remember, the motor effect is applying some current to a wire in a magnetic field to get a force that will give you a turning effect or some kind of kinetic energy. So it says this coil A to D is free to rotate inside the magnetic field. Okay, so we've got A to D here. Okay, so we're shown this view, which I guess is kind of looking down on it almost, but then we're also shown this view here, which is looking at the end of this magnet here and here. So here we've got the north end of the magnet, south end of the magnet, so that kind of makes this, I guess, the A end and the D end of this coil here. So it says the diagram shows end on looking at points A and D with the direction of the current inside the wire. Current, not electron flow, current. So as soon as you see current, we should be using our right hand. Okay, and it tells us this is the inside of the wire. So dots mean out of the page, crosses mean into the page. Okay, so it says on the diagram above, draw the direction of the force on each of the wires. Okay, so we're using conventional current here, so we're going to be thinking about our right hand. So magnetic field is your fingers, that's going to be going north to south, and this thumb is the direction that your current is flowing. So when your current is flowing out of the page and your magnetic field is going across the page, electrons are coming out towards you, then your slap is up the page. So the force on this bit should be up the page. So with the other side of the wire, magnetic field in the same direction, at this time your electrons are into the page, so your slap is going to be down the page. So your force is going to be down the page here. Okay, so putting those two on actually got you a merit. It's pretty straightforward. Once you've got one right, the other one's going to drop out pretty easily. So the next bit of this question is probably where we have to think about reading things very, very carefully. So it says our coil has got 500 turns of wire, and each side of the coil has 8.5 centimetres of wire. Okay, so the first thing that we have to do really is change this into metres. So 0.085 metres. We're told the strength of the field here, and remember, strength of the field, magnetic field, that's B that you're looking at, and you've got the current flowing, which is I. Now when we talk about coils of wire in physics, we're always talking about either a square or a rectangle. Okay. Now thinking about what we know about how this electromagnetism works, we know that anytime you've got your electrons or your current flowing parallel to the field, so in this direction, it's going to have no effect here. So there will be no force here, there will be no force being created here. It's only in the sides where it is cutting across the magnetic field that something's going to happen. So here is where we will get the force. So if it tells you that each side of a coil has got 8.5 centimetres, you've got each side being 8.5 centimetres, but it's only this side and this side that are going to matter. So you've got 0.085 here and 0.085 here. Those are the only two bits of the wire that are going to matter. So it asks us then to calculate the total force in the coil of wire. So hopefully on our formula page we can find F equals BIL. We've been given B, that's our 5 times 10 to the negative 2, given the current, which is 30. And then we've got to think about how much wire we've got, how much length have we actually got in here. So we know on each side we've got that. We know there are two sides of the coil that are contributing to this, and we know because it told us here there are 500 turns of wire. So we've also got to multiply that by 500. So if you put that in, hopefully you should get 127.5. If we round that to two significant figures, 130 newtons. And that was a merit question for that part. So last little bit over the page, it said the power is turned off and the current stops flowing through the motor, but because it's connected to the car which is still moving, the motor continues to turn inside the magnet. So effectively, there is still a section of the wire moving inside the same magnetic field before, as indicated on this little diagram. The first thing it asks you to do on the diagram above is indicate with the letter E which end of the wire the electrons will accumulate. So here we're talking about electrons, so we should be using our left hand. So left hand, we've got a magnetic field down the page. Okay, we've got the velocity of our electrons across the page, so we're going to have to do a little bit of hand contortion here. And so our slap is into the page. So slap here is going to be into the page. So the force is going to push all the electrons to that far end. And that just gives you an achieved question. Part D says calculate the total induced voltage. So we want total induced voltage in the coil of wire if it's moving at 2.3 meters per second initially. So other things we know obviously are the strength of the magnetic field, and we also know the length of the wires involved. So if we have a look on our formula sheet, we should find this little equation here. So we know the strength of the magnetic field, we were told that previously. We know the velocity that it's travelling at, 2.3, and we know from the previous page our length. It's still going to be both sides, it's still going to be multiplied by 500 turns. If we do that, we should get 9.775 or 9.8 volts if we round it to two significant figures. I think for some of you in this question you got somehow something very similar to that written down, but somehow couldn't quite get this answer out of your calculator. That was a merit question. If you didn't quite manage to get this correct and you ended up with 9.8 times 10 to the negative 3 volts, you did get achieved. That was because you hadn't quite got some of these turns involved here, if you'd only done for one wire. Last little bit was to explain how this induced voltage helps to slow the car down to rest more quickly than without it. So really this was just talking through the three, I guess, sort of laws that we've learnt, although we probably haven't really given them a name. But first thing we do know is that when we've got a moving wire in a magnetic field, we get an induced voltage. And actually, as some of you will learn next year, this is called Faraday's law, but we don't need to worry too much about that for now. But we do know that moving wires in a magnetic field gives us an induced voltage. We've always known, because we learnt this in year 11, probably even down in year 10, that from Ohm's law, as soon as we've got an induced voltage and we've got a closed circuit, we should have a current flowing. So we'll get a current being induced here. Now, when we've got an induced current in here, we can look at our, and depending on whether it's current or whether it's electron flow, we can either look at our right hand rule or our left hand rule. But what it does tell us that this will always be opposing the voltage that caused it. So when we've looked at this in the rolling rod experiment, we've looked at the fact that, you know, when we roll the rod in, we get that current being induced. Because the current's being induced, we get the electrons moving inside the rod. Again, if we do our left-hand slap rule again, we can see that the slap now is in the opposite direction to the motion. So when we get this in this particular case, the motion of the car is causing the induced current, and so the motion of the car is what's being opposed by our voltage. When we did it in class with the rolling rod, it was the motion of the rod that was being opposed. Now it's just the motion of the car that's being opposed, and so that helps it to slow down more quickly. And that was the last question on the paper, and that was an excellence question if you got through all of that. So if you kind of got one idea in there, it got you an achieved. If you got two ideas and a little bit of linking, that got you merit. If you got all the way through, and that got you an excellence.